All right, so let's jump right in. I want you to think of this as a massive cosmic detective story. I mean, the crime scene is literally the entire universe. And the mystery? Well, it's kind of like a missing persons case, except the missing person is almost everything.
So picture this. You look up at the night sky. You see all those stars, right? Well, add in every planet, every galaxy, every single thing we can see and touch, including you and me, and all of that, all of it, is just 5% of the universe. Just 5. So the big question is, what in the world is the other 95%?
Well, that's where our mystery deepens. See, that massive chunk of the unknown is run by two main suspects. They're totally invisible. The first we call dark matter, and the second, an even weirder, more mysterious force we've named dark energy.
You can think of the entire universe as being caught in this epic cosmic tug of war. On one end of the rope, you've got dark matter. It's the ultimate cosmic builder. Its gravity is constantly pulling stuff together, forming the scaffolding for galaxies and all the cosmic structures we see. But pulling on the other end is dark energy. It's the cosmic accelerator, and it's doing the exact opposite. It's pushing everything apart, making the expansion of the universe speed up, trying to tear the whole thing wide open.
So this is the big problem, right? This is the central challenge for our cosmic detectives. How do you even begin to look for something that's, well, a ghost? It's invisible by its very nature. You can't see it, you can't touch it. There's just nothing there to detect in the normal way.
Well, the trick is not to look for the ghost itself, but for its shadow. And our main tool for this is something amazing called gravitational lensing. So here's the deal. Einstein figured out that anything with mass, anything at all, actually bends the fabric of space-time around it. Light from a super-distant galaxy has to travel through that bent space-time to get to us. So if a huge, invisible clump of dark matter is sitting in between us and that galaxy, its gravity acts like a giant cosmic magnifying glass, bending and distorting the light. We never see the dark matter directly, but we can absolutely see the effect it has, its gravitational footprint, on the light from things way behind it.
Now, this lensing effect comes in two flavors. You've got strong lensing, which creates those really dramatic, beautiful arcs and rings of light you've probably seen in pictures from Hubble or Webb. But the real workhorse for mapping the universe is something called weak lensing. And this quote from Theo Schutt just nails it. He says, "Strong lensing is like looking through the bottom of a wine glass, super distorted. But weak lensing, that's more like looking through a big old window that has some very, very subtle warps in it. You can't really see the warp in any one spot, but by looking at the tiny, tiny distortions in the shapes of millions of galaxies, scientists can build a map of all the invisible stuff causing those warps."
Okay, so with this incredible tool in their back pocket, scientists can finally do the impossible. They can map the invisible. And just recently, the James Webb Space Telescope did exactly that, and it led to an absolutely stunning breakthrough.
You know, for decades, our theories and computer simulations have been telling us that the universe should look like a giant, sprawling spider's web, what we call the cosmic web. On the left here, that's the theory. That's what we thought it should look like. And on the right, wow, that's the real deal. That's the evidence. Using Webb's unbelievably sharp vision, astronomers made the most detailed dark matter map in history. And boom! There it is, a massive filament of dark matter stretching between galaxy clusters, confirming the theory with just breathtaking clarity.
And this is so important because it shows that dark matter isn't just some strange, passive stuff floating around. No way. It's the grand architect of the universe. Its gravity was the original scaffolding, the framework that pulled all the normal matter, the stuff we're made of, into these long filaments. That's where galaxies and stars were born. I mean, to put it simply, without dark matter, we just wouldn't be here. The universe would look completely different.
Okay, so we've got a decent lead on our first suspect, dark matter. But what about the other one, the even more mysterious force, dark energy? Now let's shift gears and look at the final, groundbreaking results from a huge project designed to hunt it down, the Dark Energy Survey. So, after years and years of painstaking work, the team behind this survey has given us the most precise breakdown of the universe's recipe ever. And yep, it confirms what we suspected, but with incredible accuracy. Dark energy is the boss. It makes up almost 70% of, well, everything. It's not even a close contest. And you have to appreciate the scale of this thing. It was just monumental.
We're talking about 6 years of observation, night after night, staring at almost 700 million galaxies. And the whole point was to put our main theory of the cosmos to the test. You'll hear it called the lambda cold dark matter model, or just lambda CDM for short. That little lambda symbol, that's the stand-in for dark energy.
So in the standard model, the idea is that dark energy is a cosmological constant. That's just a fancy way of saying it's a constant background energy that exists everywhere in space. Now, physicists use a letter W to describe its pushiness, and the theory predicts that W should be exactly -1. So what did the Dark Energy Survey find? They measured W to be -1.12. Now, that might not sound like exactly -1, but with the margin of error, it is incredibly close. I mean, this is a huge win for the standard model of the universe.
So, case closed, right? We figured it out. Well, not so fast. Just like in any good detective story, a good scientist always pays attention to the little clues that don't quite add up. And even though the evidence is piling up in favor of our main theory, there's this nagging little tension.
And this is where things get really interesting. It's a tiny wrinkle in the story, a subtle little clue that maybe, just maybe, we're missing a key piece of the puzzle.
It has a name, the S8 tension. And here's the basic idea. We can look back in time at the light from the very early universe, and our models use that to predict how clumpy the universe should be today. How much all that matter should have clumped together over billions of years of gravity. But when we actually look at the modern universe with surveys like DES, it's a little less clumpy. It's a bit smoother than the predictions say it should be.
So the actual measured value for this clumpiness parameter, S8, is 0.789. Now look, the difference between this and what the theory predicts isn't huge. It's not enough to make us throw the whole model in the trash. But here's the kicker. As our telescopes get better and our measurements get more and more precise, this little discrepancy, it's not going away. It's sticking around. And that's exciting. It's a persistent little clue that could be pointing towards something totally new. Maybe our understanding of gravity isn't quite right. Or maybe there are new particles out there we haven't even dreamed of yet.
And honestly, that's what makes this all so exciting. These unsolved mysteries, these little tensions like the S8 value, that's what pushes science forward. It's the breadcrumb trail to the next big discovery. And now, a whole new generation of cosmic detectives is gearing up with some seriously powerful new tools to crack this case wide open.
So let me introduce you to the next great detective on the scene, the Vera C. Rubin Observatory. Think of it as the successor to the Dark Energy Survey, but on a scale that is just mind-boggling. We're not talking about millions of galaxies anymore, we're talking billions. For an entire decade, it's going to photograph the whole southern sky every few nights. It's basically going to create the greatest, most detailed movie of the universe ever made. The amount of data, the sheer statistical power, it's going to let us map dark matter and probe dark energy with a precision that was pure science fiction just a few years ago.
So what does all this mean? It means our cosmic detective story is nowhere near its final chapter. In fact, with tools like Rubin coming online, we're about to turn a completely new page. So what's it going to be? Will we finally confirm our standard model beyond a shadow of a doubt? Or is that little clumpiness mystery going to be the thing that cracks this case wide open, leading us to a totally new understanding of gravity, of the universe, of everything? The investigation is very much ongoing.